This is an exciting live workshop. We take a 2D image and we transform that into a 3D normals. So how it's structured, basically, I will initially go through the first principles, so neural networks, normals and inductive biases. Then we'll move on to the live code experience, how you can actually make it work with Python. All the resources and the code are there. After that, we'll go on to fun experiments. We gather your data that you push through a Google Drive folder, and we just process that in real time and showcase the result so that we can have a bit of back and forth analysis around why it looks so weird or why it looks so good for some kind of satellite imagery and such. And finally, I will give you a very simple 3-step roadmap to get working system to get from 2D images to 3D models. Without further ado, let's dive onto this live workshop with Gaetano Evangelista. Welcome everyone. So this is a kind of different workshop which is more assimilated to paper workshop, where we go from images to 3D normals. I will be accompanied with Gaetano Evangelista, so this is great. So let's dive right in. At the end of this workshop, if you are part of the community, you will get the live session recording, the code with the MIT license. So here lies some specificities that we will highlight, the dataset plus the links, and also the resource curation that we touch on. So the mission is very simple. We take a single image, like this 2-bed hotel room, and we will push that into a specific kind of network to get our 3D normals. So this is the mission, single image, 3D normals. And the 3 main concepts that we touch on are these 3: neural networks, surface normal estimation, and inductive biases. So neural network, this is a kind of architecture that you are normally familiar with, where you have input and output based on neurons and layers, and here it's no different. It's a specific kind of architecture that we use, but nothing too complex at this stage. The normal estimation problem dates back some time, and it's really to try to better grasp exactly how we can have lighting affect the geometry that lies within an image. And the last stage is inductive biases. So basically, how can we inject some bias into our network in our case, so that we have additional information about from which position we see a ray of light, or what are the neighboring information for pixel, or how light behaves. These kind of things are inductive biases that we provide to our networks. These are the 3 sole concepts that you will be needing to follow along this workshop. This is just a small warning so that you're not shocked. What you will see just after is just me with another shirt, which is pink and a polo. This is because I had problem and the recording didn't work actually for all up until now. So don't be shocked, please. This is still me with a different shirt. I will leave you back with workshop now. Here were the concepts that I was briefly touching on. And this is the paper. So of course I will share with you the presentation, but basically this is the paper. We're thinking inductive biases for surface normal estimation. And you may know that next week is CVPR, and this was pushed to CVPR on the 1st of March. So it's pretty new. And it's the Tyson Robotic Lab with Guangbin Bai and Andrew Davidson that's are the author of this article. So you have an arXiv link, the project link, and the code link. And the problem is that they want to solve is this one, is that they want to improve the surface normal estimation with just a single RGB image by rethinking how they induct these biases in the process. So how they give this pixel information and rotation information so that it can work better. And in the middle, you see that it's a previous state-of-the-art approach, and you clearly see distinction between what we were able to get out from this image and what we can now get out. Before continuing, and before I forget, today we wanted to experiment something fun, which is basically making a live prediction on your images. So I will drop in a G Drive link on which you can drop in any image that you want us to process right now. Let's say that everyone should be limited to one image. Please don't set any nudes or anything. Just send a picture you would like to see the the process work on, and then it will be very fun, and it will be very cool to see what we can expect. There is a pre-processing layer, so normally you are not limited by the size of your image. Please don't send a 20 megabytes image. Make something relevant. Either you can generate it with AI, or you can take a picture of your smartphone in your environment. Just make sure that you have the rights on the image that you take. That's the second thing. So let me share with you the link of the data folder in which you can drop your image, and we'll pick it up in the process of showing the code and applying everything to see what we have. So sharing, I share the data folder, and okay, that's it. Restricted anyone with the link. So I will copy the link. Editor. Done. Okay, so let me just bring in the, it's here. I will put it here. And in the chat, you will see the Drive link. All right, so feel free to go there and drop your image there. You can put your name, or maybe, do we need a specific name convention, Gaetano, there? Or no? Okay, so very good. So just don't maybe put a specific, not UTF-8 characters and no spaces in between. This may break things for simple, stupid reasons, but that's it. So the approach, as I said, leverage a CNN, and you have this convolutional GRUs, recurrent units here, gate unit that will take it. We don't need to dive into what's happening here, but you see that afterwards you have these rotations matrix that will also improve the results. And what I was saying with this inductive biases, it's that it utilizes the per pixel ray direction to account for camera intrinsics. So they train by also giving that information from which position the ray comes in. And then they encode the relationships between neighboring surface normal through the relative rotation. So they are able to extract that and encode that into what is passed to the network, right? And then this is what you have after the convolutional recurrent neural network, this to refine surface normals. So the claim of that, I'm going very fast because we lost a little time, but at the end, if you need me to be a bit more specific there, don't hesitate. Normally, it should give better results and better surface normals and outperform the state of the art. So this is the claim. There's three elements that you see: problem, approach, and claim. This is usually when you read a paper, this should be things that you write down. This is really the base, and then after you will go on to looking at how they evaluate and what is the additional thing and what do they prove afterwards. So what do they bring on the table? And this is a very simple way to read through a paper and make sure that you don't read through and then you forget about it, but you actually retain a little piece of information and knowledge on a paper, and you can make a decision as to, is it useful for me or not? So the little workflow that we prepared with Gaetano today is this one. We will just first cover really lightly the environment preparation. At the end, Gaetano will showcase also the specifics with this specific architecture. We'll showcase how we prepare the image data sets, some pre-processing steps that are happening, and then selecting a DSINE AI model. So the DSINE is the model, this is how it's called. And using just the inference mode will not train, as you can imagine. It will take a bit too long, but the authors, they claim that they could train their model, I think it was 12 hours on a 4090 GTX. So it's very efficient compared to training much longer on NVIDIA V100 and 4 of them before with the previous state of the art. So this is why also we selected this paper. It's very close to production ready application, or at least you can really use that in some workflow that makes sense to you and that you can actually make work with a large infrastructure. The results that we will get afterwards will explore the production, and then afterwards we'll also combine depth anything with DSINE. And I think I forget a step, which is at the beginning we'll also just summarize a bit, if you remember, if you were there. If not, the part on depth anything, so going from an image to a depth image, because of course this is where it gets very interesting. AKI, I think if you can just retrieve, take out your camera, that would be good. Yeah, I don't know if you can switch off. Yeah, perfect. Thanks a lot. And that's it. So I think we can go on to the live action. So Gaetano, I leave you the floor, and I will monitor a bit the folder, the Google Drive folder, and then we can pick it up from there. So I will stop sharing, and normally you should be able to share.
Okay.
Perfect.
And can everybody hear me and you can see my screen? Awesome. Okay, I do see that people are dropping images in that folder, which is great. Florent, will you, after everybody gets their images while I'm doing this, will you put all those images into one folder so I can just download one folder instead of having to download image by image?
Yeah, of course.
And then when we're done here, and we'll just do a neat little thing where I'll run all your images on this. Hello, everybody. My name's Gaetano Evangelista. I'm a PhD candidate at the University of Nevada, Reno, here in Reno, Nevada. I'm guessing most of you are not in the US since it's 6 a.m. here, but that is where I am. Anyways, thanks for joining you. I don't know who was at my last webinar on depth anything. But this is kind of, I would say, almost sister technology to depth anything. And so we're going to talk about that a little bit. Actually, to sort of start, I'm going to go over, this was my last presentation, which was on depth anything. So basically, it takes a 2D image and it uses depth anything to create a depth image from that 2D image. Does use a transformer architecture on Hugging Face, and it's quick enough that I was able to get this up and running in real time using ROS. And I will just kind of put out there that DSINE is also a very, very fast net that will be real time, although I don't have a real time execution of it right now. Okay, so back to DSINE. So the current state of DSINE, I'm going to put that out there, is sort of a work in progress. It definitely works, and they have good instructions on their GitHub page, but they do require a lot of their own utilities and configs in order to work right now. So it's not as easy as just downloading a model, say from Hugging Face or Torch Hub, and just inferring it. You do kind of have to work within their package right now, but that's fine. So anyways, first thing we do is we get the environment up and running. So this is just system imports for doing file stuff. These are some of the important imports. Anybody who does neural nets will recognize almost all of these. So we just got NumPy, Torch, Torch Vision, PIL for image processing, and Matplotlib to show stuff. So this right here, this is all of DSINE's utilities and configs. So these aren't general Python packages. These are packages that are coming directly from, you see, close that for now, from inside of DSINE. So their configs, their utils, which are in here. someplace. Anyways, it's not important. So yeah, just know that all of these imports are a little tricky. We will share this code. I just need to put some instructions about here. All you need to do is drop this notebook into a specific folder inside of the DSINE package, and it runs fairly easily. I will suggest that you get up and running with their test files before you run this notebook, but they have fairly good instructions about how to do that on their GitHub. So one of the weird things about it and where they're currently at is I kind of have to fake an argv for the notebook to work. So normally you would do a command line argument that directs you to their config. But in this case, I basically just take the command line argument and replace it with the path to their config file. It was, I'm gonna quickly go over at the end. I tried to get a method so that we exported a model that you could all just import directly without doing all this config stuff. And it worked, but the model isn't as good as the original. And we'll talk about why at a little bit later on. So once again, this is just loading their model and their checkpoints. So they have a few different model versions. In this case, we're going to be using DSINE V02. So we load the model with the args, and we load the checkpoints for the model. So the model waits, and then we set the model to eval. So that we're not doing any dropout layers and things like that. And so I just really quickly print out Florent, this exact thing that Florent just showed graphically. This is that model. It's all based off of EfficientNet, which is a pretty standard torch model that you can use. So they just trained an EfficientNet for this, but it's nothing fancy. It's not a transformer. It's just convolution, batch normal, SILU activation. And then again, convolution, batch normal activation. Pretty straightforward convolutional net, but it does have, I'm trying to see where it is in here. It does have a little recurrency, which is a little different than your original. I don't see where it is in here, but that's okay. So okay, this is gonna be pretty quick actually. This isn't a lot going on here, but then we're gonna talk about some other experiments I've done, and maybe you guys will see some way forward that you have some experiments you'd like to do. So load the data, just glob the data paths. If you don't use glob, it's an amazing way of working with file structures. Makes your life very easy. So I'm just printing the LAN of the image path. So we're going to be working with 400 images. We can also give you access. I have some links to this data set I'm using. It's just an indoor-outdoor data set, and I believe I already put it in that drive folder that I think you all have links to at the end. Same data set I used for depth anything. So we normalize the image. These are some magic numbers, but these are actually ImageNet normalizations, which are pretty standard right now. And if you have a very specific data set that is not normal for some reason, you're going to want to get your own mean and standard deviation for normalizing your data set. But in this case, these numbers work great for the data set I'm using, even though it's not technically ImageNet. And so this is where the magic happens right here. I'm just creating a function to infer the model, pass in the image path, then torch.nograd. So we're not calculating any gradients because we're just doing inference. So basically read in the image, which is all this. So there is some weirdness if you don't work with perception data a lot. So basically reading in an RGB image, but then we're converting that RGB image from ints from 0 to 255 to floats between 0 and 1. Pretty standardized for machine learning. And then this is something that DSINE does. I don't know why, but then they basically change it from RGB to BRG. Yeah, BRG. I don't know why they needed to do that, but apparently they did. So I do it here. Now they pad the image as well. So the reason they pad the image, I mean, I didn't talk to them directly, but the reason I inferred that they pad the image is so that they could get more accurate values on the edges. So when they're running the convolution over the image, they're basically got a box that they're just running across and doing convolutions or multiplying all of those together. But you can't run the center of the box over the edges of the image. So you would get some strange values there. So they're just padding the image with zeros so that they can do those convolutions. And that's what's going on here. They normalize the image with those values that we saw up here. And then they basically get the intrinsics. In this case, we are actually using what I would call generic intrinsics, which means 60 a 60-degree field of view is average, and so we're just saying, okay, let's just say it's a 60-degree field of view, and the height is the height of the image, and the width is the width of the image. If you have your own data set and you know the intrinsics of your camera, you would want to put those intrinsics in, which is something you can pass to this. So, but these average intrinsics worked fine for this particular case. But if you really needed accuracy, you would want the real intrinsics of your camera. So this is where the magic happens. We basically infer the model, giving it the image and the intrinsics. And then we unpad. This is a fancy sort of just a line that's says unpad the image. So you take everything in the width and height, and then you change it to being from the LRTB, which is left, right, top, bottom, to the size of the original. So yeah, it's basically just unpadding the image. Then we basically detach it, put it on the CPU, and turn it into a NumPy array, and we convert it back to a image of ints between 0 and 255. Yep. And then I just returned the image and the original image, which of course you probably don't need the original image, but I just do it for display means. And then we are just going to display the image pair. This is one of the simplest but most useful functions I ever use when I'm trying to compare images. All right, then we're just going to loop over all the images in the image path. And we're going to get the image and the raw image, and then we're going to display the image. So I already ran this notebook, but basically just to show you all that how fast this all runs is we're actually going to go through 400 images, and you're going to see that I'm going to restart the notebook, and we're just going to run all the cells. And you're going to see that we actually, it gets these images real fast. So like I said, this could actually run in real time. There we go, where I can't even keep up to go down. But let's inspect some of these images a little bit. So Florent described what image normals are, or what surface. Yes, I am using a GPU. It's not super. It's on a laptop. It's a 3080 Ti. So a fast laptop GPU, but not state of the art. Yeah, so basically it's you're getting surface normals here. So the colors represent a three-dimensional vector. So you can think of it as like, it's not technically in this case RGB, but you can think of it as RGB. But instead of it being a color value, it's a three-dimensional vector of the direction of the normal. So this green is straight up. It's basically a vector pointing straight north. With this blue, if you look at the wall here, kind of being in this direction, this one kind of being in this direction. You see that's there as well. Normally, you would need to do some calculus in order to get these based off of the surfaces and the gradients of the surfaces around them. But yeah, so let's take a look at just some of the output. So this is a real clean and crisp line. So what's kind of neat and what people have had trouble with monocular image to normals before is that you get this gradient, but you don't get these nice outlines. These outlines would be blurred in here. So this one has some real crisp outlines, but it's still consistent. Like we still have these like nice gradients. These aren't harsh. So it's really, really a nice result from this one. So yeah, we'll just take a look of a few more with these. There's a couple of here that are really neat that I do want to show off. Like here, this one here, like it's maybe not the best one, but it's actually a really, really hard image to get. This one down here with the seal in the water and the glass. So it doesn't see that this is a different normal, that this is kind of curved here, but this is a really hard image. And the fact that it still gets the kid and the seal so well in there is actually really, really impressive. The other things I think that really demonstrate it well, so like underwater, is some of these hallways. I want to find that there's a few. I mean, this one's real nice, straight lines there. These benches. I mean, it's really impressive technology. And like Florent was saying, kind of state of the art. Not kind of. It is state of
It
the art
is,
for
yeah,
doing
yeah. Mm.
ocular. Here's a funny one from The Shining.
Yeah, but yeah,
In the
and
hallway.
what is also super interesting is that it's very clear if you want to go into scene understanding on the right, playing only on the normals, it's super clear to make a delineation between geometric objects. Whereas playing it on RGB image, it's a bit trickier. So there is a first thought that you can use that for segmentation tasks. So this is also something we did not explore yet. At the end here, the idea is to try and brainstorm a bit. But this is maybe a first idea, feeding in the normal image, for example, to SAM or to YOLO World, or there's architecture. I think they will pick up things maybe with better delineation than with RGB. But yeah, again, that's a try to do.
Let me jump back. So I missed a question. I think somebody asked, is this the +1? Why did I use +1 here?
On the
I
predicted
think that's
normal.
what yeah. So I think that's what you're talking about. So when they originally did the inference, they're actually using, I think, a arctan activation. So you're between -1 and 1. So this is converting that to be between, initially it'd be 0 and 2, but then you divide that and times by 255. So it's it's basically converting it from arctan to a 0 base instead of a -1 base. Yeah, good question. Okay, so anyways, yeah, these are some great pictures, great results. So let's take a look at an experiment I did to try to actually, whenever we do these webinars, I really like to give you guys like a real self-contained notebook that you can just get the notebook and get it up and running. So this is one of the cases where I didn't get you there on that because of some of the requirements of their built-in utilities and configs. And so what I tried to do is basically take their model and then export a ONNX version of that model. If you're not familiar with ONNX, it is a package and an architecture that that basically can take pretty much any model from, doesn't matter if it's from TensorFlow or PyTorch, and it packages it for production. So basically, it gets you away from needing the Torch library, which can be very large, specifically if you're deploying it on, say, Raspberry Pi or something like that, and gets you into this ONNX model, which only uses a NumPy, and really just gives you a nice small package of your model for production and deployment. So anyways, I was able to get this all up and running. This is how you would create a torch model. So everything else in this is the same. So we start out the same, but then I basically take the model and I package it into this ONNX and I export it. And what you get is this DSINE.ONNX. Onyx, I think, is how they refer to it. And then all you have to do, instead of doing all of their stuff with their config, is all you have to do is create a Onyx runtime session, and you just import that ONNX file right here, and then you basically just have your model and it's ready to run. And I did that and it worked, but what's very interesting is the model is much blurrier than the original, which was really confusing to me because by all accounts, it should be the exact same weights running in the same way. And so through some experiments and doing some research, I found that other people were having similar issues like this with certain models. A lot of times Onyx just works great. But what my current hypothesis is on this is that this is a floating point error. And so what I did is I tested the original model, basically took all the weights. I think it's in like the 100 million, not a giant model, maybe a couple 100 million, but still, parameters, summed up all of those parameters. I took the Onyx model, summed up all those parameters, and then got the difference between them. And it was something on the order of 0.002. That was the difference, but apparently that difference was enough in the floating point error between the two to basically cause the model to kind of have these blurry edges and kind of lose some of their sharp edges that we saw before. So sadly, at least at this very moment, we're not able to give you just a self-contained notebook that does all this. The one thing I will say is that DSINE is actively working on their package, and they are actively currently, I think, either getting a Torch Hub version of the model that would allow you to just download it from Torch Hub or Hugging Face. They seem to be kind of playing with both platforms. So yeah. All right, I guess the last thing I would like to show you is another experiment I did. Just out of curiosity, Florent actually suggested this, and I thought it was a very interesting idea. Is basically we took an image, and this is depth anything back again. But then I just wondered is what if we just took the normal image and put that into depth anything? So this is depth anything on the original image, and this is it on the normal image. Now, the one thing I will say is in general, the normal image looks better, but in this case, notice how this bed, like on the depth anything, it's a little, I don't know if you can see it on me casting my stream, but it's a little blurry around the edges where the normal version is real clean and crisp around the edges, and how this wall, it looks a little warped. And by warped, I mean is you go dark. That you have to think of this as depth. The darker it is, the further away it is in this case, purple in general. And it's kind of dark and goes to light and then goes back to dark. But over here, if you see, it's just a nice gradient from lighter to darker. In most cases, like if we look at this swimming pool, it doesn't work hardly at all. But that's partially because the normals actually does recognize the water as being a surface and saying that the normals of here is where the depth doesn't recognize the water as being a surface. So here it looks really good, but we do lose some of the detail from the hand. I haven't yet actually projected these DSINE to depth 2 point clouds to really take a real close examination of them. This is just all like eyes right now. Once again, this one a little bit blurrier than this one. So, I don't know if this is actually anything's gonna really come directly from this, but just thought it might be an interesting experiment and things you can play with. So the other idea right now is to kind of combine depth anything and DSINE, and to see if we can't get a more accurate sort of point cloud from combining these two technologies. So the depth anything one was really interesting. We got some very nice point clouds, but there were some issues with warping of walls and things like that. So yeah, the next step is going to be to see if we can't put these two together to make a little bit more accurate model. All right, so the first one is this aerial image, which actually looks really, really good. So yeah, people doing
So
aerial images.
we don't have the names of who sent that, but you can you
Yeah,
can, if you want, say that's mine,
let's
that's
see,
my
that's
image.
yeah. Um, the next one is a little Kirby plushie. So this one is actually interesting. So this wall is does not look as good as most walls. Most walls, it really nails them. So this one was actually, I think, like kind of a I would see like an outlier in how well it does. So that was I don't have a initial reason why that is. But yeah, so that's a very interesting one. Specifically this wall. Everything else, like even this hat, it's kind of neat that even though this is a very like almost just black blob, it actually got the shape of the
Oh yeah,
hat
yeah,
fairly
the
fairly
shape, yeah,
well.
indeed.
Yeah, so
The,
that's neat that it inferred that.
you
Another
have
real cool one.
you
Yeah.
have though in this little certification guy, it's Anthony. Congratulations! So I see 23. Congratulations if you got a
Yeah.
diploma there. But you can see little eyes, the eyes of this little mascot.
Hmm.
You can see also the smile through the normals. So this is an hallucination, eh? But that's very interesting that you can pick up this kind of information there.
Yeah. So here's like a fisheye, or actually no, this is a 360, I think, 360 camera.
Yeah,
It
equilateral
actually
angle
looks great.
projection. Yeah, yeah.
Yeah, looks real good on that one. Um, oh yeah, look at this. Look at this. Look at all that detail. That's actually kind of amazing. Little bit of weirdness on here because yeah, I think because of this tiling or something. Actually, this is you guys picked some really good pictures that are actually challenging it um for whatever reason. Like this looks great, but some of this and some of this is a little strange. Um, so another aerial image. These look absolutely amazing. I feel like there might be a lot of usefulness in aerial imagery for this.
Yeah, so
Um,
let's pause on that maybe for a
yeah,
moment. What do you guys think, um, based on these two aerial images? So this is a first thought, but from my side, when I look at both the RGB and the normals, except the white one that is a bit weird, but for the houses, it's much quicker for my perception to identify uh, the, let's say, the roof slopes than on the left side with the RGB. So I would expect a model, even if they don't work the same way we do, to maybe pick up this kind of things with much more crispier borders, which could be super interesting for segmentation tasks, like maybe just using that to detect roofs, which would be much more effective than using RGB. This is a hypothesis. But yeah, the white roof didn't work out very well. That's true. Yeah.
yeah. But you can understand why. If it
Yeah.
looks flat,
Yeah.
gonna flatten it out a little bit. But yeah, I agree with everything Florence said about the RGBD to this. So yeah, this classic rabbit looks really good. Little artifacts inside of there, but everything else looks great. This next one was really neat. Whoever did both of these. So the same rabbit from a different angle, but I don't know what you would call that. Basically meshized, or, but yeah,
Yeah,
it didn't do too bad.
this is a Stanford bunny,
Mhm.
very famous, right, for its shape and how it's used in computer graphics. So this is, for example, something very cool because if you want to check out the performances of the model DSINE, it's very easy to generate a synthetic view of the bunny as you did, and also just create a normal map based on that, based on the 3D model. And then you compare that, so you just make a subtraction to the DSINE inferred model, and you can check out the differences so that you have a ground truth, really comparison point with a 3D shape. And yeah, with the tetra or like the mesh-based decomposition, very cool example. I would have thought before seeing it that he would have picked up random noise with
Yeah,
triangles.
yeah, just ridiculousness.
Yeah.
But hi. So yeah, that was the last of them. Here, I don't know, are just some links. This is a link to the GitHub. This is the link to the data. Yeah.
I have a question.
Yeah, of course. Go ahead.
It's a very generic question that I'm trying to ask here. So basically, this 3D objects, in terms of research perspective, like how soon will it saturate? What I mean here by saturate is like there is no need of much of research into bringing this 2D to 3D images, and then basically kind of have a saturation in terms of research perspective. I mean, is it near or is it too far? I mean, so the reason that I want to understand is I wanted to explore whether can I take this direction as a research perspective so that I can get my PhD. So in that direction, I wanted to check.
Okay, so you're starting your PhD right now, or you are on your way
No,
to?
I'm about to start my PhD, still not at
Okay,
registered of the university. But so
all
before
right.
that, I was looking into the 3D objects where I mean a lot of
Yeah,
things
yeah,
have been coming out because of the Gaussian splatting and all.
yeah,
So just wanted to get your inputs of this catching on to the 3D objects. Is it a
yeah.
really
Okay.
good path to catch on?
So you have. I mean, it's super exciting currently. So Gaetano is in a in a position where he's inside his PhD and close to pushing out something super cool. But that's a fantastic experience. It's a bit stressful currently because it's super active, the area. So you have new stuff every day and a great laboratory that push out super cool stuff. So it's more about what resonates to you and what your supervisor research line is, let's say. And then after, when you have aligned that, usually you can find a sweet spot so that you have enough place for pushing out some kind of thesis, right? You say, I believe that, and you will spend 3 years trying to prove that. As to how it comes with 3D, you have three main tracks. You have everything that is linked to 3D data acquisition or data generation. This falls within image to 3D. Then you have the track around 3D data processing and 3D geometric processing, sorry, as an overall systemic view. And then you have all that is linked with semantic injection, understanding, scene understanding, which is super active toward tasks like semantic segmentation, instance segmentation, open vocabularies to detect some kind of elements and tie that all, and know how to do inference. So I would say, whichever way you pick up, you are sure that you have a massive field, exciting stuff to search, which is very competitive currently. So you just, I would advise, especially in the beginning, to choose something where you don't feel like you're in a heavy competition. But that's tricky to find.
Yeah.
I hope I answered your
Yeah.
question.
If I can add on to it, yeah, it's sort of what Florent touched on. It's about finding your niche. There's definitely plenty of little places to still be working on this 3D data and push out papers and get PhD through it. You know, maybe you are the person to do it, but just don't think that you're going to be like the person who trains a you know, a world-changing neural net. But there's a lot of niche spaces to do a lot of work on this still.
Yeah,
Okay.
and it's very easy to experiment with stuff. So especially in the beginning, experimenting, but trying to get already onto some kind of low-level implementation. That's very cool, but without falling too much onto just pushing out code. That's not what is asked from a researcher. You are more there to delineate what is existing, to push something new, and to showcase a proof of concept. So yeah, exciting. And Raphael, yeah, I agree. I don't know, Gaetano, if you can move up to the equirectangular image. It's, I think your camera froze, but I don't know. Okay. Yeah, this I would really like. I think we can do that. I will do that after. Like passing that, for example, to Sam and passing the normals to Sam. This is a bit tricky because you see that you have a change in normal estimation on the walls. It's like going wrapping a bit, whereas on the color side you have kind of flat white. But the ground very good, and the ceiling looks like also very good.
Yeah, I just wanted like to get like the or to identify the great arcs, and I think this with the kind of like a segment anything model is able to get me those arcs from the equirectangular image. Yeah. So it
right.
detects very well the ceiling, the floor, and then stuff in between, and also is able to kind of with these gradients getting a kind of notion that the wall is curved on the, for example, on the right side. It's not something that is okay. This is a flat region, which is not. So basically,
it's not a flat region.
Yeah. So it's a flat because it's a wall. It's a wall, but since it's we are in the perspective, it kind of creates this like the vanishing point like bubble there.
Yeah.
And,
but yeah, that's the right idea. No, I think very good. If you want to extract the edges, even just a classical off detection or corner detection may work better on that kind of image.
Because the floor has a lot of, that's one of the examples that I found of the internet. I couldn't paste anything that I'm working on, but the floor is like with a lot of noise, with simple RGB kind of edge extraction. It will lost a little bit on the tiles that we can see on the floor. Even the light on the ceiling, we might get some problems there. But here, even that sometimes tiles on the floor are kind of similar with the wall in terms of color. And it is able to kind of segment, let's say, the things.
Yeah, beautiful.
Yeah.
So Anthony, I will be doing my master in cartography. Yeah, very cool this winter. Hopefully playing more 3D in the geospatial. Yeah, exciting stuff. So don't hesitate to reach out again if when you start things you feel a bit lost or you would like to have a bit of an idea where it will be most beneficial to you. I would be happy to help you get there. And David, the food image is interesting in showing a failure mode. Tile pattern. Oh yeah, right. Confuse the model. Yeah, indeed.
Yeah, no, this one's really weird.
Yeah.
I'd actually like to explain because I've seen tiled walls that look great on other samples. So yeah, this one is I got a lot of questions about this one. One of my first questions, and I don't specifically think this is true, is I wonder what would happen if I just rotated this. So instead of being like sideways, if it was actually more accurate to what we would see as people. But yeah, definitely a failure case that did real great with the food itself.
No, but I think based on the architecture, because they extract this rotation around local features of rotation. I think definitely there is an issue if you take a picture that is not upward oriented, more or less. So I think rerunning with a rotated thing may yield different results. That's solely based on what I saw on the paper and the architecture. This is one of the limitations I noted to myself when I read it. So that may be one of the fix there why it does this, but yeah, just this is just a roadmap. If this is the kind of technology that helps you, that is very simple into 3 stages, what I will recommend. The first one is exploring single image to 3D, then moving on to multi-image to 3D, and then to 3D deep learning. So for the first thing, what I will do is I will send you a package with 3 main course video. You have the Python code and such. If you are the only thing that you will need to do is get on, but normally you are all on it, the mailing list. And then you will receive that, I think, Wednesday, if I manage to bring that all together in a nice, convenient manner. The second thing is, depending on where you are, the course 3D reconstructor. This is if you want to automate workflow to generate 3D assets from multiple 2D images, where you have image-based reconstruction, 3D Gaussian splatting, and I'm pushing out how you can also get asset stores up and running. And then you have the 3D deep learning course, but this is more focused at the moment on 3D semantic segmentation tasks and supervised AI architectures. But there are some cool new updates that are coming in your way there, so that will expand it to instance segmentation and other very cool stuff. So this is it for just the next 3, let's say, steps around this kind of topic. Single image to 3D, you will get it in your mail. And if you want to push a bit more multi-image to 3D, there is the course 3D reconstructor, and 3D deep learning, the course 3D deep learning. Congrats for following up until there. Please, if you did not already, just take the code, take the resources, and take the time to re-implement it, and actually use your proper image with your implementation to push this concept of 2D image to 3D normals with this DSINE work that is actually very, very interesting. I hope you learned a lot here. Stay tuned for the next live workshop. In the meantime, don't hesitate to build your skills with the LearnGeo Data Academy.